Oh, oh. Can you share? We're gonna finish some of the questions in the booklet today. That's it. End of module 2. Today. Yeah. Which means, yes, we are going to have a test just for module 2 next week and the week after having a half year. But I'm going to cover some of the questions. We're going to do some problem solvings. So let's do it. Mm-hmm. Good morning, Anna. Oh. Yeah, I'm on YouTube. All right. Okay, before we move on to some of the questions that about the gas flows, actually, I need to revise some of the contents that we're learning through. So I'm going to give you some summary of the whole module 2, beginning from like a very early, like a mole concepts. Okay. Okay, awesome. All right. In the beginning of the module 2, we started learning about something about the moles. Okay, as you remember, the moles is all about the packaging unit. That is a really small number. Really like atoms are really small, significantly small. So we're given the moles in the packaging unit of the Avogadro's number. Hope you remember that 6.022 times 10 to the power 23. So when we say I'm having a mole of something, it means that I have this many, 6.022 times 10 to the power 23 of something too. So in a way, we were able to find first that number of moles N was able to be found by the total number of the something, like in the molecules and atoms, divided by Avogadro's number as well too. Or this can be re-modified as, if you're looking for the total number of the atoms and molecules, it can be refound by N times the Avogadro's number. Okay, and we also learned about like how to balance your chemical equations with including the states. So states is something that's very important coming out. So I hope you remember all the rules of stating the states, the gas, liquid, solid, and aqueous states too. Also, we learned about the solid state. Solid state. Generally, that comes in the that's not gas, in the grams of something, in the grams for the standard units. We know that we are also able to find that number of moles N by mass over molar mass. For this kind of working out, make sure you show the relevant formula as well as all the relevant working out. That you need to show how you got the molar mass, showing all the you're using your periodic tables, so which shouldn't be a big issue. Then we also learned about the solution. When something comes in solution, that in the aqueous state, that we have a various type of the concentration units. Do you remember some of the units that we learned? Units? Anything? Ooh, we had things like grams per liter. We had like a milligrams per liter. We have the ppm. This is basically milligrams per kilogram, so milligrams per liter as well too. The units, we also use the ppb. Sometimes ppb, let's write it down. ppb, known as micrograms per the liter. Percentage, it could be the weight per weight or the volume per weight, the weight per volume or volume per volume. As I emphasize that, make sure show that relevant percentage of what. There's something coming out in the year 12 as well. ppm, you will see quite a lot in the year 12. So you won't be told, like this unit will not be given. So memorize that as, milligram per liter is basically ppm, which means You should be able to convert in gram per milligrams by times that 10 to the power of 3. If you're going opposite, milligrams to gram, you can times 10 to the power minus 3. All right, and also, the most importantly, we learned about mole per liter. Some of the unit conversion you need to have, if you want to convert the mole per liter to the gram per liter, then you need to times, because you kind of convert and think about the number of moles about a mass over molar mass. So if you want to convert the mole per liter to the gram per liter, you need to times the molar mass of the compound, or if you want to convert the gram per liter, mole per liter, you need to divide the molar mass of that. This is something that's a very useful tool that you will actually get a question, lots of questions related to the unit conversions. Sometimes they're giving you the concentration in gram per liter, and then I'll ask you to convert it back to the mole per liter to maybe the percentage. I don't know. Okay. From there, we are also able to know that from especially the mole per liter, we know that N, C, concentration is all about N over V. That means, hello. Thank you. That means that we are able to find the number of moles by C times the concentration times the volume units. Okay. And a kind of application of that, we also learned that in the terms of dilution. Remember that, guys, dilution means that we do not change the total amount. Do you remember, like in the vitamin C tablet, I put 1, I put extra water. It doesn't mean that I get the less amount of it. If you drink them all, you still get the same amount. So C1, V1 equals to C2, V2 is generated from, because we are keeping the constant values. For the skills test or the scientific skill, like if you're learning up to here, you may get some questions about making the standard solutions. In the standard solution question, you may get like write a method down. You may get the method. Okay, it's not so complicated, and we've done some practicing here, so I hope you get the good method. 2, you may get some calculation questions involved too, which is not too bad. All right, that's a solution chemistry. That's something we learned. So remember the 2 formula. The N equals to, actually 3, N equals the mass over molar mass, N equals CV, and also N equals to the total number of the molecules divided by the Avogadro's number 2. That's something we learned. This is all we learned before we start the gas laws. Then, let's move on to the gas. The gas or the gas law. Gas state is having the volume of the liter volumes instead of the gas. We believe that gas has the least dense, which means that the particles are parted the further. What that means is, solid state, you would see like a solid, the particles are kind of packed together like that. Liquid state or solution state, you get some distance between them, and they are able to move down like in between them. But gaseous state simply means gas particles are further apart, so you actually can get like some of the volumes of it. You actually get some density of those. And then we learned about different characteristics of the gas called the gas laws. And asked to remember some of the gas laws using this. 1, VP. 2, Charles on TV. 3, Gay PT. So let's talk about the BVP. It means that according to Boyle, this is called the Boyle's law. That's called the Boyle's. This is the Charles' law, and that's a Gay-Lussac. Okay. Yeah, can you leave that there? Okay. See you later. Okay. So BVP stands for this. That volume from the V and P, volume and pressure is indirectly or inversely proportional to each other, which comes to V times P gives you a constant value, which is a K. Charles on TV stands for the T and V, that temperature and the volume are directly proportional, gives that T on V or V on T is the constant value too. Gay PT or the Gay-Lussac law stands for the P and T, the pressure and the temperature is directly proportional as well, giving us that the P on T is also be the constant value. Now, those constant values are not the same values. It's basically, I'm just saying, oh, there will be a fixed value. So you remember that for the BP, we can make in the B1, P1 equals to B2, P2. And we kind of use the ratio values of that too. But most importantly, it's kind of limited because in certain stages, like in some situations, we only get a change of once and it will get the rest of the constants. We can get a change of manys. So we actually can, the combined gas low, that's giving you that, combine everything there, giving the formula that P1 V1 over T1 is equals to P2 V2 over T2. Okay, all right. Considering about this here, this is giving you some really good ratios of the gas, the factors. But it also carries some limitation, and this is something that you need to know. This does not, there's a no, and the number of the mole or amount included. Why is that a problem? Because we know that according to Avogadro's law, Avogadro's law, we know that the number of mole or the amount will be directly proportional to the volume. It's simple, really simple. If you have a lot of the gas particles, obviously you're going to expand them more so that you will get the more greater volume too. The combined gas law doesn't really include anything information about number of moles or the amount. So in a way, this is a really good formula that we can use to find the volume, pressure, and the temperature in terms of the ratio of something, if you have an increase or something, but it will be limited in terms of like it's not really included the number of moles. And I'll describe that as this is not quantitative. That you may get something changing the various changing situations too. We're not able to find that changing in that volume, pressure in that way. And this is the reason why we kind of combine these two together later on. Now, so let's talk about a bit more about the Avogadro's law, okay? According to Avogadro's law, we know number of mole will be directly proportional to the volume. So we learned that at the STP as in like that's a 0 degrees Celsius and 100 kilopascal. Then the kind of standard temperature and the pressure. We've learned that for 1 mole of any gas, takes 22.71 liter of the volume. Just confirm. Yeah, 22.71 liters. So that's for the STP for 1 mole to 22.71, which means that this we can write it as molar volume. This is called a molar volume at STP. Gives you out that 22.71 liter per mole. Remember this unit, guys. This means per mole of the gas at the STP, we have 22.71 liter. If I have 2 moles, you got to times 2. 3 times 3. So it's got to go kind of proportional, which is following the Avogadro's law. So we can rewrite it that as, so therefore, we can find that number of mole, again, is equals to the molar volume. So volume, the total volume of the gas you have, divided by molar volume at the given temperature and the pressure. This is third. Sorry, how many? 1, 2, 3. This is the fourth equation for the number of moles that given the STP. Now, at the SLC, which is more commonly we use, this is the 25 degrees Celsius and 100 kilopascal. Basically, the room temperature and the standard like the pressure that we're feeling now. We're now going up in the mountain, going down the sea. That's basically like in the sea level. That's what we believe. That for 1 mole of any type of gas, remember this statement, any gas, I don't care that whether the gas is heavy, like in a really big or small, like a CO2, even for like methane, some like in alcohol gases, doesn't really matter. It takes the same volume. It takes the 24.79 liter. So make sure you remember this. I know the value will be given on your formula sheet. So the molar volume at SLC, I should say, SLC is therefore 24.79 liter per mole. Please remember the unit. It's not the mole per liter, it's the liter per mole. You gotta get a question today. They are asking about how we're gonna convert the units back to. Just like what we have done in here, from the mole per liter to gram per liter. If you want to convert it back a unit from liter to the mole to mole per liter, you need to go the reciprocal, basically inverse of that. So that is still using the Avogadro's law. Does that make sense? So we learned up to here, and we started learning about more about this. So going back to the combined gas law, combining all the Boyle's, Charles, and Gay-Lussac's, looks great in terms of giving the good ratios. It's always to be constant value. We understand the point. But as I said, there's not including the number of moles, and therefore it's not so quantitative. Means that we are not able to find how many, or what's the volume in some of the given situations too. This is why we kind of developed the combined gas law, combined with the Avogadro's law again, giving you that ideal, the gas law. This is the formula giving you that PV equals to nRT, where the R is the gas constant. There's 8.314 is a gas constant value. So, and we can get from here, the N, number of moles, can be calculated by PV over RT like this. So this is what? The fifth and the last formula that you need to memorize. Yes, you really need to memorize those formulas. This is the last formula you need to memorize to find the number of moles, but this is only applicable for the gas state. For the gas state. Those number of moles, and this is for the solution aqueous state. That's for the solid state. That's for any of those, okay, just in terms of the molecules. How many? 1, 2, 3, 4, and 5. The reason why you will find the modular 2 or the chemistry is hard because in the exam, we're kind of mixing up all the number of moles formulas. Sometimes you're given a solution, sometimes you're given a gas, sometimes you're given a solid. So you have to read the question very carefully, especially units of data where you're given. If you're given the grams, that must be N equals to M over molar mass. Mole per liter, solution. If you're given a liter, you may think about this as a gas state using this or either that. Does that make sense? Okay. And for the ideal gas laws, again, for other like some gas laws over here, I didn't really mind that if you didn't convert that into standard units. But for the ideal gas law, units must be in the standard. So what that means is the pressure would have the kilo kPa must be in that unit. Volume must be in the liter. The N, obviously, that would be the number of moles. At the T, it's not the degree Celsius, the Kelvin. All right, kilopascal, do you remember some of the unit conversion from what? 1 atmosphere, 1 bar. So remember this, 1 atm is equals to 101.3 kPa, or 1 bar is known as the 100 kilopascal too. You sometimes get like a tricky units of the pressure, so you still need to know how to convert that. Millimeter mercury, it's kind of rare, we still can get that too, which is 1 over 100 too. The liter volumes, if you're given the milliliters, just convert it back, you know, that milliliter into the liter. How do we do? It's always from milliliter to the liters, you times the 10 to the power of 3. Going back, do a bit, oh sorry, the other way, 10 to the minus 3 times 10 to the power of 3, from big to small. Moles, no comment for the moles. Moles be basically moles. You can find any of those methods to find the moles. Kelvin, all right. How to convert the degree Celsius to the kelvins? remember that 0 degrees Celsius is equal to 273.15 Kelvin. So you need to memorize the value, and 25 degrees Celsius would be 298.15 Kelvin as well too. If you're kind of confused about those units of the kelvins, you will get the formula sheet, the chemistry formula sheet, okay? You can find that the volume of the one gas at 0 degrees Celsius, that's giving you the 2 Kelvin units too, okay? So it's okay if you forget about it, especially in the exam conditions, use that. Okay, don't forget that you have it in your formula sheet, but don't just look too much and look for that. You should know where that exact information is. So this is where we're up to now. Started from Chapter 1 of the Module 2, all the summary up to here. All good? Okay, so please remember all the different units of the number of moles. Next week's topic test, yes, you will get the mix of many of those number of moles questions. And in year 12, it's not just finishing the year 11, year 12, you got to get a mix of everything. And then they will even telling you what you're getting. It's getting more complicated. You actually need to understand the situation, like what's going on in there. But if you kind of completed this, if you kind of understand all the contents here in the year 11, year 12 calculation is still not easy, but it's doable. Okay, if you don't understand the module 2 and start to attempt like a year 12, the calculation year 12 would not be doable. It's actually really difficult to understand what's going on in there. So you need to build up just some of the muscles to solve the questions. Any questions? Okay, you can copy this down. You can take a photo if you like to. I mean, this is a big summary of everything of the module 2 then. All right, let's move on to the some of the questions in your workbook that we couldn't finish last week. We're gonna finish all the workbook questions and then move on to some extra questions today. Okay, page 161. We did that some of the questions there. Okay, page 161 in class exercise 5.3, please. All right. Let's use the some stoichiometric calculation involving with the gas. So, question 1. Calculate the volume of the carbon dioxide in liters produced when 2 kilos of propane is burned completely in the oxygen to produce carbon dioxide in the water. The gas volume is measured at SLC. So, question will specify what kind of conditions that you have. Remember that as soon as you hear the SLC, you should remember that, okay, the molar volume must be 24.79 liters per mole. So, first step, any type of stoichiometric question, any of the stoichiometric questions, start with the balanced chemical equation with the states. Yes, states are very important. So what we have, the propane is known as C3H8. Okay, propane. That's a bit of organic chemistry, by the way. You don't worry about for now. Okay, you will learn that next year. This propane gas goes through the reaction with the oxygen gas, O2 gas. Producing that is complete combustion, so producing the CO2 gas and the water. Just memorize that as a template. So always the complete combustion, the reaction producing the CO2 and H2O. And then you're just going to balance this one out. Starting from the number of carbons, we have a 3. So we need to have a 3 of the carbon in here too. We have 8 hydrogen, which means that we need to have 4 of the water. So making that what? We have in total the 6 oxygen, and we have a 4 oxygen, making 10, so times 5. This is now balanced. Check the states. The reason why I'm putting the H2O gas is because combustion is hugely producing lots of the heat. So when you're combusting like a fuel, you actually can get the liquefied water that can all get vaporized. So practically saying that should be the gaseous state. Then, after you're writing down the balance equation, start with what you're given. Or write it there, rewrite all the relevant information you have. So you're given the mass of the propane is given you as 2.00 kg. This is given. And it says it's completely in oxygen to produce. So it is all burned. Then you got to check that in here. Oh, okay, we get to some mass in kilograms, which we don't really prefer in chemistry. So what we do, we're going to convert it into the grams. So you may just go like to 2,000 grams, but you can just, if you're not confused that, just write a kilo to the grams. You just 2 or times 10 to the power 3 grams like this in terms of unit conversion. Okay, this is kind of useful, especially if you got a really some like odd numbers in like a kilograms too. And then what we do, we can see that mass is keeping the grams. That means that we are able to find the number of moles. Always find the number of moles with the relevant formula. As we get the grams, you got to bring mass over molar mass. That'll be 2.00 times 10 to the power 3. That divided by, show all the relevant working out. 3 times 12.01, which is the molar mass of the carbons. 8 times 1.08, that's the molar mass or molecular mass of the the hydrogen. Then put that in your formula. But, okay, this is an important tip. After you do that, calculate the molar mass value. 3 times 12.01 plus 8 times 1.08. You'd get 44.094 on the 2 times 10 to the power 3 here. Leave your number mole value in the exact value forms rather than you put it in your calculator, get to some sig fig or the decimal points. Okay, this is some of the techniques that the examiners love to see, because when you start writing some decimal point, that means that from the next calculation you may get some significant error. So I just leave that as this for now. We can just write at 2,000 if you like to. And then what we do after is we're going to look up this, because we want to know the gas in the carbon dioxide, the gas volume, the volume of the carbon dioxide produced, so which means this one in here. This is time to bring it out, the reaction ratio there. So according to the reaction ratio of propane C3H8 to the CO2, always write it down, is 1, 2, 3. 1, 2, 3. So solving this kind of ratio formula, this is giving you that, therefore, the N of the CO2 is 1 is equals to 3 times N of the C3H8. Use the method. Use the method. You will never get it wrong. Then, as we got the number mole of the C3H8, you can just times, so that are 3 times 2,000 divided by 44.094 mole. Again, that's the exact value too. Does that make sense up to here? Okay, then let's going back to the question. We need to find that volume of the carbon dioxide, which is the gas state. So the volume of the gas is found by, remember, the N times the molar volume. From that kind of modified volume over here. Okay, N equals to volume gas divided by molar volume, so that this can be done. Let's write it down, molar volume at SLC. This is 3 times 2,000 divided by 44.094. That times that. Molar volume at SLC, that's what? 24.79. Just substitute the value in. After you're showing that working out, then use your calculator. Okay, so 3 times 2,000 divided by 44.094. That time 24.79, just in the one go, you'd get 3,373.24 liter. So show that some of the kind of exact value first of all, and then matching up to your given sig figs. You're given, in the question, you're given 3 sig figs, means that you need to change that value into 3 sig fig values. This is 3,370 liter in 3 sig fig. Unit and the sig figs will get marked for every single questions. Which means if you forgot about like to put down the sig fig values, then you get a lot of the marks deducted. And that's painful actually. Like you can see like mark loss because of the just for that. So this is kind of basic, like some kind of more basic, but it's most important, like some template, a guideline to how to deal with the stoichiometric questions. No limiting reagent yet. We gotta get some questions as well. Questions? Everyone good? Okay. Now, could you try for then question 2? Question 2. You can use the same formula that I gave you in the question 1 for the propane combustion, so just leave that for now. So for that question, we still have a propane, which is combusted, but this time it's an 800 gram rather than around the 2 kilo. So we have 800 grams of propane combusted. It means we can find that the number of moles in the same process basically. No, but make sure you show all that relevant working out, including showing the formula and showing this calculation process as well too. This is something that's very important. We would love to see that every single time you're dealing with these documentary questions. So just leave that and some exact values, because if you divide that, you get some of the decimal point. I don't want to say some points. And then what we have to think about from here is, yes, we got to do some find the carbon dioxide. So let's copy this one down according to, again, to the molar ratio of the reaction. The ratio of the propane to the CO2, that is 1, 2, 3. You do know N of the CO2 is then the 3 times N of the propane again. That is 3 times that, so 2400 divided by 44.094 mole. I just timed the 3 on the top of the 800. Okay, up to here is kind of exactly same template kind of working out. But what you have to notice that from the question 2 is, you're not given the situation of the SLC or the STP. Instead, you give it 60 degrees Celsius and 200 kilopascal. In that case, it is not a standard, it's not a lab condition anymore. So it means that you need to use the ideal gas flow. So let's write it down, the pressure that you're given. Pressure is given as 200 kilopascal. Check that, whether that's a standard unit or not. Kilopascal standard unit we follow, so we can just leave that as it is. But temperature, which is given as 60 degrees Celsius, is not the standard unit. Even though we use it in their everyday life, we have to convert it into the Kelvin by 60 plus 273.15 Kelvin. That is basically 333.15 Kelvin like this. After you get it over here, bring that, the ideal gas flow, the PV equals to nRT. Then leave that formula for the subject to the V. Then V is equals to nRT over P. Well, the R is the gas constant 8.314. So substituting all the values in, 24 and about 44.094. That times that 8.314. That times that temperature. Now we're given that 333.15 divided by the pressure that we're given, 200. And then time to put in everything in your calculator. So we have 400 divided by 44.094 times that 8.314 times 3.15 divided by 200. You should get 753.792 for some kind of exact decimal points. Check that we have how many sig figs you have. We only have 1 sig fig, by the way. 800 is not the 3 sig fig, that's our 1 sig fig. So you may need to, even though I hated to write it down, this would be 800 liter in the 1 sig fig then. So in the some school exam and most of some kind of well-designed exams, you're probably given a more specific sig figs, but not the 1 sig fig, by the way. 1 sig fig is something we try to avoid because, as you can see, that's a huge gap between 753 to the 802. So I'd rather go for 2 sig fig, which is 750 milliliters. But that's the method how we use the ideal gas flow then. Okay. Now, could you try for 5.4, please? The butane questions again. Butane is known as C4H10, is the butane gas. So question 1 and 2, both of those, please. Write it down, all the relevant working out, and you may share one formulas between two. I'll leave that, the working up for now. And for the combustion of those hydrocarbons, you may get that again in year 12 too. That's exact style of questions too.
Do you have to memorize the butane?
Not yet. Not yet. For year 12, yes. Yes, Richard, you did know. Now you know what the butane is. You can count that. For the alkane, it's good to remember that alkane has a general formula of the CnH2n plus 2. Okay, that's actually kind of how we, this is something that was useful that I don't want to. But for now, use that. I'll give you about 5 minutes, so we're going to go through the questions together then. Okay, start with the balanced chemical equation with the states butane and requires 2 butanes for 13 oxygen gas, producing 8 carbon dioxide and 10 water molecules like this. For the balancing, as I said, leave that something in the element, the pure form, and the loss, because that's easy to control, easy to modify. So start with something that's more complicated and matching all the atoms or elements. Then you may get the balancing quite easily. All right, we're given the 300 grams of that. The question's asking you again the volume of the carbon dioxide. So what we're given is they fall from the number mole, for the given mass, 300, that divided by molar mass. You get the 300 divided by 58.12 mole for the exact values. Then write it down as according to the reaction ratio of the butane C4H10 to carbon dioxide CO2 is giving you as 2 to 8. 2 to 8. So I can just simplify to 1 to 4 straight away, which gives you that, remember this, the N of the CO2 is equals to 4 times N of the C4H10, like that. So that means you just need to times 4 on that, so giving you 1200 divided by 58.12 mole by times of 4 to the 300. Okay, and then what you're given is it's a SLC. So molar volume, you can just copy the molar volume at SLC. Is given you as standard lab condition 24.79 liter per mole. Therefore, the total volume of the CO2 gas must be N times the molar volume, that is 1200 divided by 58.12, that times 24.79. So 1200 times 24.79 divided by 58.12, you should get 511.837. Given that, again, 1 sig fix, I just leave that in 500 liter in 1 sig fix then. Okay. Question 2. Sharing the same formula of the some chemical equation of the butane, that we have butane burnt again, and then this time we have a given different mass. So N, let's start to go like here. N of the C4H10 can be found by mass of a molar mass. Now this time we're given 5 kilos. So 5 kilo must be converted back into the grams. So 5 times 10 to the power 3, or 5,000, divided by, show that all the working out to 4 times 12.01 plus 10 times 1.08. Then you may get the 5,000 divided by 58.12 mole. Leave that for the exact value too. Then, as we need to find the carbon dioxide, according to, or I can just write N of the CO2 must be 4 times N of the C4H10. This is how you can shorten your working out as well too. Show that according to the reaction ratio like this. Okay, you may write that method or this method, but I recommend writing this one, especially showing all that the ratios, especially when you're dealing with something really complicated or more complex numbers. Okay, that's relatively easy to figure out. So that means that we can have 4 times that, just giving you 20,000 divided by 58.12 mole of the carbon dioxide. So in that condition here, we're given that the pressure is given as 400 kilopascal. Let's write it down again. Temperature is not the Kelvin, so 40 degrees Celsius, which is same as 271. Adding that 273, that would be 313.15 Kelvin. After that, bring that PV equals to nRT from the PV equals to nRT. Okay, just write it that P equals to nRT over P straight away if you like to. Then N, we give it 20,000 over 58.12 times the R, gas constant, 8.314, times the T, 313.15, that divided by the pressure, 400. Then just put that in your calculator, divided by 58.12 times 8.314 times 313.15 divided by 400, you'd get 2239.787. Fix that in to give it a sig fix of 3. This is then 2240 liter in 3 sig fix. Got the answer? Okay, so basically all the same methods they can use in here. Okay, for the next question, let's skip the question 1 and 2. Let's go for this question 5.6, page 165, please. Let's have a look at these questions now. Question 1, 25 grams of the hydrogen gas and 100 grams of the oxygen gas are mixed and ignited. The water produced is collected and weighed. The equation for the reaction is given as 2 hydrogen gas. Let's write it down again. 2 hydrogen gas plus O2 gas goes to 2H2O. You don't have to copy this down. It's given basically up on top. The question's just asking you, hey, what is the limiting reagent straight away? Then, for any type of the limiting reagent, guys, okay, start with defining number of moles of all the reactants. So you're given 25 grams of hydrogen, 100 grams. Check that gram means that the mass given. Then you can find that N of the hydrogen gas can be found by mass over molar mass. That's given as 25.0 divided by 2 times 1.08. For this time here, we gotta find the value in some, so you can approximately get to some value. So 25 divided by 2.016, you'd get 12.4 mole is given. Okay, same process for the oxygen. O2 can be found by mass over molar mass again. That would be 100 grams, 100 divided by 2 times 16. So 100 divided by 32, you get 3.125 mole. That's a given. That's given. Yep. So after you calculate the number of moles, what you need to do is you got to choose one of those. I'm always recommending like choosing something with a less coefficient value. When we have 1, choose that. So for the given oxygen gas amount, the N of the H2 required. So think about it here. For 1 oxygen, we need to have 2 hydrogen gases. So I'm going to take that as I have 3.125 moles given. Then just calculate it, then how much of these hydrogen gas that are required. It can be found by 2 times N of the O2 given. That is basically 2 times 3.125, giving you 6.25 mole required. Does that make sense? Okay. For matching here, and for this number of mole of oxygen, I need to have the hydrogen, that's 6.25. So what you see there is amount of hydrogen required, we need to have 6.25, is much less than amount of hydrogen gas you're given, provided. This means what? After the reaction, we know that hydrogen gas will be in excess, it will be left over. Therefore, the oxygen gas is the limiting reagent. Practice that as many as you can. You will get tons of those limiting reagent questions. And this is kind of working out, you need to show every single time. First, find the number of moles of the given the reactants. You choose one, but I prefer to choosing that something with a lower coefficient value because it's easy to calculate the required amount. And then find the required amount for the chose one, the reactants, and then compare it to the given amount. Then you can figure out if you have too many of that left over, that means the opposite would have been a limiting reagent. If you have less than what we required, that is a limiting reagent then. That's for question A. B. What is the volume of the water vapors at the SLC then? Okay. Now SLC, okay, and we get to find it here. So what we know about the limiting reagent is this will get all consumed. We got to use all the oxygen gas, and we got some hydrogen gas left over. We're not interested about hydrogen gas this time. We're only interested about oxygen because